All right, so welcome to Math 140 Calculus 2. And what I want to do today is I want to continue with the applications. And so today we're going to talk about solving differential equations. And then after we talk about solving differential equations, we'll actually apply it to an extremely important problem, a problem from mathematical warfare. And you can use this analysis to look at the Battle of Trafalgar, which was one of the most influential, one-sided conflicts, I think, in the history of warfare, in terms of just the outcome this had for world history and just how lopsided the result was. And again, no mathematical model is going to be perfect. The more features you add, the more difficult it's going to be to solve. We are going to do an extremely simple model for the real world. But why do you think I'm going to choose such a simple model? Why do you think I'm going to greatly simplify things? So we can understand and we can solve it, right? If I put in all the different features, you would have to use incredibly advanced theory, or it might be so bad we can't even solve it in closed form and we have to resort to numerical simulations. When we talked about the Fibonacci numbers and trying to estimate the probability of, say, so many blacks, so many red results in a row when you spin the roulette wheel, we could actually solve the recurrence relation. But if you don't know how to do that, just write a computer code, simulate 100 spins a million times and see how often you get 5 in a row of the same color. And so even if you can't solve it theoretically, you can often approximate the answer well enough for all practical purposes. So I want to be able to just talk about how to exactly solve something. So I'm going to do a simple model which captures a lot of the key features. But then if you really wanted to use this in the world, you would then start adding additional practice to it. One of the things that's a little bit different about naval warfare back then is you can actually capture a ship in the middle of battle. You could have a boarding party go over, and now all of a sudden the ship is on your side. So the number of your ships in the battle is not necessarily a constant. It could actually be growing. So we'll ignore some stuff like that in a simplified model, but these are things you would have to take into account. Nowadays, you're not going to have boarding parties and taking over a ship. The ship is going to be sunk. All right. So what I want to do is I want to start talking about differential equations. I believe we looked at Newton's laws of motion. We looked at if the acceleration is constant. We talked about how you would solve velocity. It's related to acceleration. The derivative of velocity is acceleration. Velocity is related to distance. The derivative of distance is velocity. And so we solved it in one dimension. We just shot the rocket up or the ball up. We solved it in 2 dimensions where we had gravity acting down. And we talked about what happens as you change the radius of the Earth. Well, the radius of the Earth is so large that if you move up a few feet, you're not going to effectively see any change in the force from gravity. Yes, there is a change. The force is a little bit weaker if I start an electron on the desk, but not enough to really make it worthwhile, especially given that I have the electronic devices here and I can easily step on them. So we might as well assume to first order that in what we're doing, the Earth's gravitational attraction is constant. If you want to travel to the moon, not a good assumption, right? And you'll eventually hit a key point where the moon's gravity has a stronger influence on you than the Earth's. And that's psychologically, it was a major milestone to finally reach a point like that. All right, so there's a huge amount that you can do with differential equations. So differential equations talk about how things change, often with respect to time. And you can have many different things all interrelated. How many of you have seen, say maybe like the ideal gas law? So this is where we're citing into multivariable calculus. Anybody remember the ideal gas law? PV equals nRT. So pressure times volume is the number of moles times the gas constant R times the temperature T. And the ideal gas law is the law which describes the motion of an ideal gas. And an ideal gas is that which is described by the ideal gas law. So you're going to be a little bit careful in terms of how circular are your definitions. And then, of course, the question is, are there situations where maybe the law breaks down? If we really compress things and maybe get into a plasma, but in general, it's going to have large ranges where it is applicable. And you can ask, well, what if the volume is changing at some rate? How is other things changing? You can have all these different relations. And the more variables you have, the harder it's going to be to solve things. And so there's an entire class, not surprisingly, called differential equations, where you learn how to solve differential equations, and you see how you can use them to model a variety of phenomena in the real world. For a lot of them, it comes down to solving and finding antiderivatives. Well, that's one of the goals of this course. So it's always nice to get a sense of, why am I spending an entire semester learning this material? What can I do with this now that I know? Well, one thing is you can solve systems of equations. Now, when you're trying to solve these, you need techniques. And this is the same as when we have techniques in integration. So what are some of our ways to integrate? What could we do? By parts, one of our favorites. What else? Partial fractions, usually not one of our favorites, but good to know. U substitution. U substitution is usually pretty popular. Trig substitution, which is really a special case of U substitution, but because of their very strong lobby, they get their own name. Okay, so we have different techniques for integration. And these results all come from nice, differentiation rules. Similarly, there are ways to solve differential equations. So I'll just talk about some of them. So let's say I give you, dy dt equals a constant c. So this is probably the simplest differential equation we could try to solve. Y, the derivative of y with respect to time is constant. So we could write this as, the integral of, dy equals the integral, I'll let the constant be a. So I'll say dy equals a dt. And if I integrate both sides, there's two ways people like to do this. They like to do it like this, or they might write the integral y goes from y initial to y final, dy is the integral from t initial to t final of dt. Or you could maybe integrate y goes from y naught to maybe y of t dy equals the integral t maybe goes from 0 to, obviously I've got to be careful because I'm integrating with respect to t, I can't use t as this letter. And this is why people often get, I hate doing this, right? You might have to use a different letter for your variable. I need to leave fewer. Interesting. Okay, so let's integrate. So let's look at this. So what function has derivative y? Actually, has derivative 1, has derivative 1. I can write this as just 1. So it's just going to be the function y. What function has derivative a? Not 1/2 t squared. What function has derivative a? 1/2. If you have t squared, the derivative of t squared is going to be, a is a constant. Right, a is a constant like 5 or 7. I'm integrating with respect to t. It's at, right? It's just at. But we have to be a little bit careful. When I integrate 1, it's y, or it's y plus any constant. And when I integrate a, it's at plus any constant. So I should really have a constant on both sides. Well, if I have constants on both sides and they're arbitrary, I can just move the constants all to one side of the equation and call that a new constant. So rather than putting a constant on both sides, maybe c left on the left, cr on the right, and then having cr minus cl, I can say it's at plus c. And this is almost enough to determine y. So you could write this as, y of t is at plus c. If we know y of 0 equals b, then we would get y of t is at plus b. So if I know an initial condition, I can solve for y. So this is the simplest thing I can give you. The next is, what if I give you dy dt is some function of t? Well, I could play exactly the same game. I would get, dy is just f of t dt, and I would integrate. Right? What's the integral of 1 dy? Y. So you get y, and then let's let capital F be an antiderivative for little f. So what would the right-hand side become? So if I let capital F be an antiderivative for little f, what is the integral of f of t dt? What's the indefinite integral? It's just capital F at what point? Just what's my argument? A t, right? And then what else do I have to put in? Plus c. So we would get y of t equals big F of t plus c if y of 0 equals b, then y of t would equal f of t plus b minus f of 0. So can we solve problems like this? What do we need to be able to do to solve a differential equation of the form dy dt equals f of t? So if we can do something, we can solve any equation of this form. What do we need to be able to do? I mean, it looks like I wrote down the answer. What must I be able to do for this to count as a solution? So where's the main work? Where did we have to think? Let's look line by line. We have the integral of dy is the integral of little f of t dt. Is it easy to integrate 1 dy? What about integrating f of t dt? Is that easy or hard? Hard. In general, it's going to be very difficult. So works if we know big F. If we don't know big F, this is very hard. So for example, I could give you, dy dt is e to the t squared. So then we would have the integral of dy is the integral of e to the t squared dt. Good luck. There's no nice antiderivative of that. We can come up with infinite series expansions. And we can, try to play games like that. We can say, e to the u is the sum, n goes from 0 to infinity of u to the n over n factorial. So e to the u, so e to the t squared would be the sum, n goes from 0 to infinity of t to the 2n over n factorial. So the integral of e to the t squared dt would be the integral of the sum, and goes from 0 to infinity of t to the 2n over n factorial dt. What would you like to do to the integral of the sum? Have an integral of a sum. What would be wonderful to be able to do? I'm sorry? Yeah, do the sum of the integrals. You want to switch the order. So you need to develop some advanced mathematics that allows you to say, when can you switch orders? You can't always do that. So if you can, switch orders if you can. And then you would have the sum, n goes from 0 to infinity, of the integral of t to the 2n dt, and I'll put the 1 over n factorial over here. What's the integral of t to the 2n? So what function has derivative e to the 2, oh, sorry, t to the 2n? T to the 2n plus 1 Anything else? Over 2n plus 1. So this will converge. We get an extra factor of t, not a big deal. And we even have a 2n plus 1 in the denominator, which makes things even smaller. So this converges for all t. Fortunately, we've talked about how do you determine if a sum converges. We've talked about the ratio test and the root test and the comparison test. So we have plenty of ways of showing that this sum converges. So we have a way to solve this differential equation. We have a way to get what big F of t is. This would be big F of t. It's just, it doesn't have a nice closed form expression. It's not going to be something like a nice polynomial. But you have to remember, a lot of things that you think are nice are not. How do you calculate sine or cosine or exponential? These are infinite functions. These are infinite sums. We call them nice functions and we give them a name. I could give this a name. I could call it Bob. Or if Nike's willing to give me money, I could call it Nike. I don't mind selling out, for enough money, right? Just because we gave it a name doesn't necessarily mean it's easy to compute with. Now, this sum converges very rapidly. So if I wanted to estimate things, I would only need a couple of terms to have really good convergence. So this is how I would solve, something of this form. If I give you dy dt equals, f of y and t, this is much harder. Because now I've got y's and t's mixed up. But imagine we could write this as f1 of y times f2 of t. So this is called separable. So we could write it as a product of two functions. How might you try to solve this now? So we could start as we did before. Dy is f1 of y, f2 of t dt. But if I try to integrate, I've got y's on both sides. So what could I do? It's bad that I've got y's on both sides. So what can I do to fix this? Yeah, so what would the next line become? I'm sorry, dy over, right? Divide both sides by f1 of y. So we would get dy over f1 of y equals f2 of t dt, and now just integrate. And then it all comes down to, can we do the integral on the left? If we can, we're in great shape. And then we've got to handle the integral on the right. And if we can handle that, then we're in wonderful shape and we've got everything solved. So for certain problems, you can actually do these integrals. But it reduces this to calc 2 problems. I can solve equations like this. Then you can start to get more involved equations. Right. We should have time. So I'm going to do a fun problem that my physics professor showed me right before we went for Thanksgiving break our freshman year, so we would have something to talk about over Thanksgiving. So define the symbol integral by the integral of f means the integral t goes from 0 to x of f of t dt. Okay, so I'm just introducing notation. By integral, I just mean shorthand. Take whatever function this applies to and integrate from 0 to x. Okay? So I want to solve the integral of f equals f minus 1, or the integral t goes from 0 to x of f of t dt is f of x minus 1. Anybody have any thoughts about what function might work? When you integrate the function, you basically get the function back minus 1. So I'm integrating from 0 to 1. So maybe I want a function that's 0, so that's 1 at 0. And maybe the integral of the function equals the function. Any guesses? I'm sorry? It's related to a trig, or better, it's better to say the trigs are related to it. So do you know any function which is its own integral? So maybe e to the x. So I plug in f is e to the x. Yeah, the integral of e to the t is just going to be e to the x minus e to the 0. So f of x equals e to the x works. So you can just check that by direct inspection. What I'm about to do now is as much illegal mathematics as I can in 5 minutes. It can all be justified in advanced math and trying to solve an equation like this. So I have integral of f equals f minus 1. So this is the same as f, I'm sorry. F minus the integral of f equals 1. I just brought 1 over to the other side and I brought integral to the other side. Everybody comfortable with this? This will be a nice way to review some of the stuff we've seen in class. This is the same as 1 minus integral acting on f equals 1. Because 1 acting on f, I just multiply f by 1. I get f and, okay. If you had 3x equals 5, how would you solve for x? Divide by 3, or multiply by 3 inverse. If you had 7x equals 5, what would you do? So let's multiply by 1 minus integral inverse on both sides. Okay. Well, if I consider 1 plus r squared plus dot dot dot, that equals 1 minus r inverse if the absolute value of r is less than 1. So using that analogy, f equals 1 plus integral plus integral integral plus integral 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 plus dot 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 acting on 1. You might be a little bit concerned, can I use the geometric series formula here? Let's go piece by piece. 1 acting on 1 is 1. The next is I have the integral of 1. Well, what's the integral of 1? The integral of 1 is the integral from 0 to x of 1 dt. What does that equal? That equals x. The next one is I have the integral of 1. The integral of 1 is the function x. So integral of 1 is the integral of the function x, which I'll now write as just t. So the 0 to x dt, that becomes what? Not 1/2. It is the same as 1/2, but I don't want to say 1/2. I don't want to say 0.5. Not 1 over 2, close to 1 over 2, 1 over 2. Oh, 1 over 2 factorial. I want to write it as 1 over 2 factorial x squared. Because I'm trying to get e to the x. What's the next one going to be? Integral of 1. Well, integral was the function 1 over 2 factorial x squared. So I now have the integral from 0 to x of t squared over 2 factorial dt. You can see I'm going to get a t cubed over 3. And the 3 hits the 2 factorial and gives me a 3 factorial. And this will give me 1 over 3 factorial x cubed. So you can actually make this argument rigorous. It's a really interesting calculation when you're trying to solve an equation like this. There's a whole slew of techniques you have to develop. And this is now, how do I invert an operator? So this is just giving you a sense of really what's out there, what kind of equations do we have a chance of solving. So now you're completely different. You're going to the Battle of Trafalgar. So how many of you have seen or read anything about the Battle of Trafalgar? To be interested in more details, there's links. I'm not going to go through too much. It was a battle during the Napoleonic Wars. The British on one side and the combined, fleets from France and Spain on the other. So if you look at the strengths, the French and Spanish had 33 ships of the line, 5 frigates, 2 brigs, 35,000 men. The British had 20 27 ships of the line, 4 frigates, 1 schooner, 1 cutler, 20,000 men. And if you look at the casualties, you know, a little over 4,000 killed on the Franco-Spanish side, 458 on the British. There's some wounded, a couple of men captured, but the amazing one, 21 of the ships from France and Spain were either, I guess, were captured, and 1 ship was destroyed. No ships were lost on the British side. It was a crushing blow to Napoleon in terms of just the complete destruction of the naval force. So Britain has always been an island, and for them, the Royal Navy has been of tremendous import. There was a lot of great discussion in the years leading up to World War I on how much of the budget of Britain should go to its Navy. And they were very concerned about what other countries were building. And for a while, they wanted to have a fleet that was strong enough to handle the next 2 strongest navies in the world. And it eventually reached the point where they could no longer do that. I think one of my favorites is they were trying to decide how many dreadnoughts to make. I think Parliament wanted, 6, the Navy wanted 4, and after discussions, they settled on 8. But when they were talking, they just realized that the situation was far more dire than they thought, and that the conservative estimates would not be enough in the years leading up to World War I. So this was an absolutely amazing victory in terms of just how lopsided it is. No ships lost or destroyed on one side, 22 out of 33 captured or destroyed on the other. And since 21 of them were captured, that's actually increasing in own strength. So the British fleet, amazingly, was stronger after the battle than before the battle. So the question is, how do you model, modern warfare? And how do you use this to determine what strategy should you use? And I hope that we will never have to apply this, in our homeland. But if you look at what's going on in parts of the world right now, calculations like this are being done. So here's basically an artist's conception of how the battle was beginning. So you have the ships of the French and the Spanish, arrayed over here, and the British are coming in with a main force and a slightly weaker force. And the idea that the British had, that their leader, Lord Nelson had, was to have a majority of their ships come in and split off a good chunk of the fleet from Spain and France and attack them. And then have a smaller portion of the British fleet whose job it was to just stall the remaining enemy ships and delay them, keep them out of the battle so that the main part of the British fleet could turn on a subset of the ships from France and Spain, dispatch them, and then come back to the rest of the battle. And the idea is to use overwhelming numbers. So this is a beautiful article, Mathematics and Warfare by Manchester. And in the old days, basically, it was hack. You run out, you have all the people fighting, and for the most part, one of my soldiers kills one of your soldiers, vice versa. So if we have 2 armies of about 1,000 people, you expect everybody to obliterate each other out. Another way of looking at it is because of the way the linear fighting was. If you have people running in lines, it doesn't really matter how many men I have. What matters is how many men do I have at the point of battle. And so if I have 1,000 people, let's say I fight one army of 500, and then after I fight them, I move on to fight another army of 500. If I start off with 1,000 people, after I fight an army of 500, how many people do you expect I would have at the end? 500. And then if I fight the next army of 500, how many would you expect I would have at the end? 0. Everybody would be wiped out. So in your classical warfare, basically one soldier kills one soldier. There's really not much of an advantage in having a bunch of people coming in together. There's some, but it's not as overwhelming in modern days. In modern days now, if you have a huge fleet and you can attack the enemy one at a time, you bring all your guns to bear, destroy the first ship. All your guns to bear, bring the second ship. And if you can do this, you can often do this without getting any casualties or minimizing the number of casualties you get. And so this is the modern condition where basically you say that the more forces you have involved in the battle, the more damage you can do. And so the differential equations is we have two fleets, the blue fleet and the red fleet. So this way we don't have to make any country feel bad for losing. So we will say B is the blue fleet, R is the red fleet. And the rate of change of the blue fleet, dB dt, is equal to minus R times C. So can somebody tell me how they would interpret this? Is the blue fleet getting larger or smaller over time? Smaller. Makes sense. There's a negative sign. It should be getting smaller as the battle rages. Okay. Again, we're not allowing ships to be captured in this model. The amount that the blue fleet is decreasing is proportional to the number of red ships. Does that make sense? The more red ships you're facing, the more destruction you have. And the proportionality constant is related to how effective are the ships. So what might you want to assume about C and K? So C might be the effectiveness of the red fleet, K would be the effectiveness of the blue fleet. What might you assume about the two combatants? They're equal. But if you think about the situation, maybe the British forces are more effective than the French forces. Can you give me a reason? I'm sorry, I can't say British. Maybe the blue forces are more effective than the red forces. Why might the blue forces be better? I'm sorry? Oh, these are equation 1, equation 2. That's all. Sorry. Just equation 1, equation 2. So if you think back, look, let's forget the colors. Let's think back to Britain for a moment. Why do you think the British ships might be more effective than the ships from France or Spain? Well, then one is potentially you have better leaders. You have leaders who have a better knowledge of naval battle. Okay, that's one reason. Why else might they be better? Why might one country have better forces than another? They've dealt with more things in the past. So the British might actually have more experience in shipbuilding. For the British, a fleet is not a luxury. And before World War I, the British delegations to Germany, as Germany was building up its naval force system, look, you don't really need a powerful navy. You're a land country in Europe, your army is your strength. For us, we need our navy. And when we see you building all of these ships, we can't help but get worried. So the British might have more experience in building ships. If they have more experience, they might actually have ships that have greater range of guns. They might have faster speeds. They might have better trained crews. And so there's a lot of reasons why you could be more effective. Imagine that you could shoot accurately 2 miles more than your enemy. How much of an advantage could this be? So why? Why would that be such a big advantage? And they can't shoot back at you. So if you can shoot 2 miles further than they can, and let's say you can travel faster than they can, you can keep firing at them while they're out of range. Anybody ever see Spaceballs? It's a spoof of Star Wars, and there's a beautiful scene when Lord Helmet, the Darth Vader guy, is attacking the combined character of Han Solo and Luke Skywalker. And he just holds him on his helmet, and he's so short that his lightsaber doesn't reach him. He's just swinging away, but he can't make it. And so if you can fire at a greater range, with a greater accuracy, and you're faster, you can just keep shooting all of the enemy's ships before they can hit you at all. So in this case, what would your expected losses be? If you have greater range, greater accuracy, and greater speed, minimal to maybe zero is you just keep your ships right out of range. In the modern day, aircraft carriers are the most important ships in a lot of fleets. And there's often orders of shoot to kill if any armed planes get anywhere near enough to launch a missile at a carrier. Just because, you cannot risk having anything come that close. So carriers will always be surrounded with escort ships and with planes flying it to make sure nothing gets in the tow zone. And so here, depending on how much more effective you are, you actually have the possibility of having no damage if you can always just keep firing. If you're the other side, you might just have to have your ships come in directly. What kind of ships were these back then? How did they move? Sail. So you can't always take the course you want. And so depending on how the winds are, there could be some real issues in terms of maneuvering into position. Okay. So here's a beautiful plot of just using some of these models. In the first, we have an army of 1,000 blue fighting an army of 500 red. And you can see over time, the 500 red gets destroyed. But the number of blue doesn't go all the way down to 500. It goes down to, it looks like 8 something. Chat. And so rather than having the blue go all the way down to 500, the blue go down to 800 something. And now they turn and they face the other 500. So before we talked about an army of 1,000 faces an army of 500, goes down to 500, faces another army of 500, goes down to 0. Now you fight with 800 something against 500, and you finish with 707. That is a remarkable difference than ending with 0. So here, by using the ability of compound attack, okay, it was 866. Okay, the text is down here. It says 866. So now you have over 700, over 70% of your force survives, which is much better than 0. So this was the main idea behind Nelson's strategy. I do not think he actually sat down, wrote the differential equations and solved them, but just had some instinctive knowledge of the ability of, we can have a large body of our force attack a large body of theirs, while some of our other ships do a delaying action. And so, not surprisingly, you can write all of this down in Mathematica, and you can write and you can solve, and you can find as functions of time what the answers are. And so I'll just briefly talk about how you try to solve something like this. So dB dt is minus r times some constant c, dr dt is minus b times some constant k. So this is a little bit harder than what we've studied before, because now we have 2 different variables that depend on time. We have b depending on time, and we have r depending on time. Before we just had y. So we have dB dt equals minus r of t times c. Oh, yeah. That is minus c times r of t. And we have dr dt is minus k times b of t. Well, what I want is an equation involving just b and t. I don't want b's and r's together. How could I get rid of r of t? What could I do so I could then substitute for r of t? Well, I've got dB dt is minus r minus c r of t. I want to replace r of t with something. I don't know what r of t is in terms of b. What do I know that's related to r of t that's a function just of b? dr dt. So what could I do to the equation dB dt equals minus cr of t so that I could then use my knowledge of what dr dt is? What could I do? I want to get a dr dt because I can replace dr dt with just a b. So what should I do to dB dt equals minus cr of t? Take what? Yeah, take the derivative with respect to what variable? So take the derivative with respect to what variable? These are functions of what? What are they functions of? B is the number of ships as a function of time. R is the number of red ships as a function of time. I'm taking the derivatives with respect to time. I've got dB dt, dr dt. What should I take the derivative of both sides with respect to? With respect to t. right? So take derivative with respect to time. So then we would get d squared b dt squared. Minus c is a constant. So I would just get minus c dr dt. And I would get d squared r dt squared is minus k db dt. So I know the second derivative of b is equal to minus r times the first derivative of r, but I know what the first derivative of r is. So if I substitute, I get d squared b dt squared is minus c dr dt is minus k b of t. So I get d squared b dt squared is ck times bt. Okay, so I'm looking for a function where if I take two derivatives, I get my function back multiplied by ck. So this is a second order differential equation. I wouldn't say it's my favorite method, but it's not a bad method. It's the method of divine inspiration. I talked about the method of divine inspiration this class before. So you basically you rub your chin a little bit, you look up to the sky, you go, aha, and then you write down the answer. So what is the problem with the method of divine inspiration? Yeah, it may not come to you. You may not be divinely inspired, but in a lot of problems in math, it doesn't matter how you get to the answer. If you have the answer, if you write it down, you can then check. Well, if I believe I know what b of t is, I can check and see, does d squared b dt squared equal ck b of t? I want to be careful and I want to make sure that I get everything. Okay, so anybody have any thoughts about a function whose second derivative is almost itself? It differs by the constant ck. Well, the problem with sine is going to be periodic, right? As the battle happens, what should be happening to b? Yes, it should be going down. So if it's periodic, if I do something with sine or cosine, not only yes, all of a sudden, the ships just reappear. But you're on the right track. It's something related. It's something that sines and cosines are related to. What's the inverse of log? It's the exponential function, right? It's almost as if, I don't know, earlier today, when we were talking about something like this, it's almost as if there was foreshadowing, that there was some thought done in this lecture. To try to get this on your radar screen. So let's try b of t is an exponential. What exponential should it be so that its second derivative would be ck times itself? So I have to take two derivatives. So let's try b of t. Let's just try some unknown. Let's try a of t. Then db dt is a e to the at, and d squared b dt squared is a squared e to the at is a squared b of t. So what should a squared equal? So a squared equals ck. So what does a equal? Anything else? Or negative square root of ck. So the solution is b of t is, say, a1 e to the square root of ckt plus a2 e to the negative square root of ckt. And it turns out this is the solution. So a differential equation of degree 2 should have two free parameters, and that's my a1 and a2. Now, if you think about it, one of these a's has to be 0. you think of which one has to be 0. Is it the one that goes with e to the square root of CKT or e to the negative square root of CKT? What do you know about the number of ships as time passes? It's diminishing, or at best, it's staying the same. You know, if you have a great commander, we're not allowing ships to be captured. So what would the term e to the CKT, what would that go to as t goes to infinity? Infinity. Even if you're capturing ships, you know, you don't have shipbuilding yards in the middle of the battle turning out. A1 has to be 0 from physical grounds. A1 equals 0 as the number of ships does not increase. And there we go. And so you could use something like this to maybe argue that A1 is 0. But you could be mistaken here. Maybe this equation only works for a certain amount of time because the battle doesn't go on forever. Maybe not. You know, he does not go to infinity. So, you know, this is to just show you how careful you have to be in your analysis. So we might just say, oh, A1 has to be 0 because otherwise, well, once I defeat all of the red forces, the battle doesn't continue, and the number of red ships, there's now negative 15 red ships attacking us. Right? So there's going to be some final time. And so maybe the constant in front of e to the CKT is just really small. So maybe you can still have it. So you just have to be careful. All right, so this is, I think, you know, a really nice introduction to what comes next in mathematics. This shows you a little bit of linear algebra. We have systems of equations. Shows you a little bit of multivariable calculus. You know, we've got several different things going on here. Shows you solving differential equations, and a lot of this is related to the integration techniques that we've developed. It shows you all of our stuff on sequences and series. You know, when do we know that things converge? Okay. So again, lots of great stuff here. Plus, there's a lot of wonderful applications of this. And that, you know, depending on how the math is, this can influence how you choose your strategy. This idea of, well, if we have concentrated forces, it's much better to put everything together, finish the first one, and then move to the second. I will end with one of my favorite examples. So my wife is a professor of marketing, and a lot of her research, at least in previous years, was devoted to waiting times and trying to understand wait times. I actually look at similar things. I look at spacings between times. You're waiting until the next time, or other things in mathematics. How many of you have ever been to a bank? How many lines does the bank have? 1. And what happens? It gets long, and then the next teller who opens says, okay, I'm free now. Next person in line, come here. When I was young, banks often had a line for each teller. Why is it better to have 1 line than, say, 4 lines? If you have somebody who is a high maintenance person with a very complicated time-intense order, they can knock out an entire line for a long period of time. And then everybody in that line gets frustrated because there's nothing worse than realizing I chose the wrong line. That line's moving so much better. And you just get very upset. It's not a pleasant experience. The average wait time is independent of how many lines you have approximately. The standard deviation, the fluctuation, is much smaller when you have 1 line. You know, you're going to have people, when you have 4 lines, you have a much better experience. And you're going to have some people who are going to have a much worse experience. And so this helps minimize those extremes. So there's a whole idea of just trying to model, wait times. And how would you model something like that? In supermarkets, we don't have 1 line feeding in. Why not? So why would supermarkets be so different than banks? So one thing is so they might give you a little bit more time to look at that. I think it's also maybe the size of the carriages and whatnot. If you had like one big line and all this crossing in. But it's just interesting to think about why do some places do it one way and other places do it other ways. All right, so this is a good place to stop. Have a good rest of the day.